Dear colleagues, it's my pleasure to introduce Alexandr Lobashov with his today's talk, Hessian Geometry of Latent Space and Phase Transitions in Diffusion Generative Models. Please, Alexander. You're welcome.
Hi, everyone. Today I will talk about the study of latent geometry of different generative models, mostly concentrating on diffusion generative models. So this talk is based on the publication Hessian Geometry of Latent Space in Generative Models, which is accepted at ICML this year. This is done in collaboration with Dmitry Guskov, Maria Lachenko, and Mikhail Tam. So what is the idea of this talk? We will talk about geometry of latent space in generative models. So firstly, we need to define what is a latent space. So we assume that we have a high-dimensional data manifold X, and so X is a whole space. For example, for images, this is space of all pixels, and M is our data space. For example, in the case of images, X are just whole pixels, and M is some real images with strong spatial correlation for close pixels. And also, we assume that we have a generative mapping. So we have a space which I call Z. It contains, for example, for generative adversarial networks, it's just samples from real normal distribution. And usually we assume that this is lower dimensional space. And then we apply generative mapping, and we obtain a distribution of images. And actually, if we have some coordinate system in this latent space, then our generative mapping induces coordinate system on the space of all images. For example, if we could take two images which generated by some 2 points in a latent space, then we could create interpolation. And this interpolation in the space Z will give us some curve in the space of images. So here we have, for example, one sample from Gaussian and second sample from Gaussian. We could draw some simple line, and after applying generative mapping to all intermediate latents, we will obtain a curve in the space of images. So our generator could be any generative model, for example, diffusion generative model or generator in generative adversarial networks. And then if we have this generator, then we could define a metric on the space of images on this manifold M by just using our Jacobian of our generative mapping. So our generative mapping is a function from Z to X, and Jacobian is just derivative of generative mapping with respect to the latent variable Z, and metric. So I have some not good notation because this is metric and this G is generative mapping. So metric, remaining metric on this manifold M is just this product of Jacobian. So we have this metric in the case if this generative mapping is deterministic. And if we have a metric, then we could introduce for any curve in the latent space, we could introduce its length. And if we fix some images and corresponding latents on the both ends of this curve, then we could introduce a geodesic curve. So if our latent space is Euclidean space, then geodesic are always straight lines, and straight line in the latent space introduces some curve in the space of images. So this is a particular way to introduce notion of smooth interpolation between two images. Yeah, and geodesic, as I mentioned, this is curve with minimal length. And length is defined by our Riemannian metric. Okay, so now let's talk a bit about generative models. So we have main types of generative models. First are variational autoencoders, and second are a generative adversarial network. So what is bad about this model? Why now everyone uses diffusion models? The main problem is mod collapse, which occurs for both GANs and variation of autoencoders. So, but mostly for generative adversarial networks. What is mod collapse? The problem is that if we have some data set, for example, of human faces, and we train a generator to generate these images of those faces, after training, we will have samples of some good quality. So if we look at it by our eyes, we see that these images are good. They are similar to the images of real people, but there will be a problem of diversity. So if we generate a lot of different faces, after some generations, we will observe that these samples are quite similar. And if we look at the data set, we will see that in the data set, usually we have a better diversity of samples. And this is main difference between traditional generative models like GANs and variational autoencoders in comparison to the modern diffusion models, which have a much better mod coverage. And actually, both VS and GANs, they have very interesting properties of their latent space. So as I already mentioned, both GANs and VS, they have a latent space, and we could just take some two random samples from Gaussian noise, convert them into an image, and then since both generator in GANs and VS is some neural network which is fully differentiable, and as soon as we gave it a single latent vector, it is fully deterministic, then we could compute this minimization problem using autogradient in PyTorch, for example, and this problem and finding of geodesic is solvable for small generators and discriminators. And people ask a question, what if we just take latent noise and we'll consider a straight line in the latent space, and it will give rise to some interpolation between images. This is the first way of interpolating between two images. And second is way is we just take this Riemannian metric, compute curve length, and compute geodesic as a result of minimization problem. So would these curves will be similar, or will it give rise to a completely different interpolations? And actually, what was found, for example, in the work of Shao in 2018, is that geodesic found in this way are extremely close to just linear interpolation in the latent space. So, for example, here examples of, I think top is linear interpolation, and second is geodesic, which was obtained by solving minimization problem. And we see that the movement of faces and the whole interpolation is quite similar. And the same is for other data set. And this is quite interesting that if we have a data set which consists of like similar images, for example, only domain of faces or only domain of handwritten digits, we will see that linear interpolation will always be close to geodesic interpolations. And this was discovered also for generative adversarial networks and for many other architectures, but not for diffusion models. So actually, if we have a geodesic and it is a straight line, it means that we have on this manifold of images, we have a notion of covariant derivative, and our parallel transport is trivial. It means that if geodesics are straight lines in this coordinate system, which is given by our latent space, so if geodesic is linear, it is the same as having a flat connection on this manifold of images. So the important point is that if we have some latent space, it defines coordinate system, and if straight lines are actually close to true Riemannian geodesic, it means that we on this manifold we have locally a connection or covariant derivative operator which is flat. And okay, let's mention this more strictly. So there are several conditions which are equivalent. First is every geodesic on M is a linear path in some local coordinates. So here we have a path on our manifold of images, and we have these coordinates, and in these coordinates the geodesic line is actually a straight line. So this is the first condition. Second is that this is equivalent to having a torsion-free flat connection on this manifold, and this is just a reminder on what is torsion-free connection. So usually you could think of it as a covariant derivative along a vector field, but if you like coordinates, then you can think of that you have a Christoffel symbols which are symmetric with respect to lower indices, and its Riemannian curvature tensor is always zero. Okay, and also there is equivalent definition that we have a coordinate chart on M such that all transition function between coordinate charts are just affine function. So this is another equivalent definition. Okay, and if we have a connection which is flat, then all Christoffel symbols will vanish, and we actually have only the second derivative of our curves, which is zero. So it means that we have a straight line as a geodesic if our connection is flat. So in other words, what is interpretation of these results of Shao et al. And a lot of similar work? It means that the data which supported on some single mode, its latent space could be modeled as a affine manifold, which admits some flat connection. Okay, and also, what do we know about affine manifolds? So first of all, they have a flat connection. So also it means that if we take a second derivative of some scalar function, for example, here consider a convex function psi. So on a general Riemannian manifold, Hessian of a convex function, this is not invariant with respect to Riemannian coordinate transformations. Because if we take second derivative, then after changing coordinate chart, we will have coefficients which are multiplied by Christoffel symbols. So we so covariant derivative of a scalar function will be invariant, but just second derivative of function, it is not in general invariant with respect to coordinate transformation, because we need to take actually second covariant derivative. But in the case of affine manifold, we don't have any connection coefficients, and actually this equation 11, which is Hessian of a convex function, will be invariant with respect to this coordinate transformation. So actually, we could consider a more general structure. So if we have an affine manifold, then actually we could introduce a triple consistent of manifold, flat connection, and metric, which is a Hessian of a convex function. So this triple is called a Hessian manifold. Or strictly speaking, an affine manifold is which is also a Riemannian manifold, is called a Hessian manifold if in local coordinates this Riemannian metric could be expressed as a Hessian of some convex function. And this notion of Hessian manifolds give rise to the notion of Hessian structures, Hessian geometry, and this is closely related to the information geometry of probability distribution, and also this is closely related to statistical physics and thermodynamics. For example, this function, which is a convex potential, could be interpreted in statistical physics as a free energy of a thermodynamic system. We will talk about it a bit later. So all this was about a deterministic generative model, which takes a point from a latent space and generates a single sample. For example, single image, like a generator in GANs. But we know that diffusion models, what they also maybe critical feature is that they allow a stochastic sampling regime. So if we have initial noisy image, in diffusion model we solve a stochastic differential equation, and as a result we will get some distribution of images for a single initial latent. So it means that it is better to work with a more general case of stochastic generative models. And if we have our latent space, then generation is not a single sample. This is some conditional distribution. In deterministic case, it will be just delta function centered at this sample which was generated. Okay, and in deterministic case, we had a pullback metric on our manifold of generated images, but now we don't have any convenient manifold. So every point in our latent space corresponds to some probability distribution. And we need actually, in order to introduce geodesic for this case of stochastic generative model, we need some notion of metric in the space of probability measures. And actually, there is a natural way to define such a metric, which is Fisher information metric. So usually people define it as the following equation 12. So we have averaging with respect to this parameter of this score function. For example, for normal distribution, this Fisher metric will be inverse of the covariance matrix of a normal distribution. So if we introduce a metric in a space of probability measures in such a way, and one could check that this is indeed a positive definite field of tensors of second rank, and this is symmetric. Fisher metric then is a Riemannian metric on the space of parameters. And,
excuse me, only you're taking an expectation with respect to X, right? So you can sample from this distribution.
So how to estimate it practically? I fix an initial latent variable. In diffusion model, it's just initial starting noise. Then I apply iterative denoising with different seeds, and I will obtain some data set of images. And then if I can estimate this score function, but this is different score function, because in diffusion models, what is called score function is logarithm of p, and gradient is with respect to x. Here we have a gradient with respect to t, and if we know estimation of this gradient, we just average it with respect to our samples. So this is one of the way to estimate it for some stochastic generative model. Okay. Actually, there is a family of probability distributions for which this Fisher metric actually becomes a Hessian metric. So actually, what is idea now? We know that for generative adversarial networks, we have geodesics, which are almost straight lines in the latent space. And we know that on affine manifold, we could introduce a structure of Hessian manifold. So it means that we have a Hessian potential, and so we have convex potential, and Hessian of it is a metric. The question is, so if GANs have such a nice latent space, maybe we could introduce a convex potential on the latent space of GANs, and it will be the probability distribution of exponential family. So the main property of exponential family, which we are interested in, is that Fisher metric for this exponential family distribution is just Hessian of logarithm of this normalization function. So this function for exponential family is also called free energy in the case of statistical physics. And its Hessian is indeed a positive definite metric. And our question is, maybe all these generative models which learn a single mode, maybe they just implicitly learn in some exponential family model. So they're actually not some arbitrary complex function which maps noise to data, but they somehow implicitly learn this distribution of exponential family. So, and this is a question, main question actually of this talk, whether this is true and in which extent this is true or not. Okay, and actually what we could say about a general Riemannian manifold. So, because Fisher information metric is actually defined for any manifold, so we don't have any assumption on the properties of latent space, on existence of some flat connection. But question is, if we have just some Riemannian manifold with some Riemannian metric, will it admit a Hessian structure? And the answer to this question is actually positive for two-dimensional analytic and smooth manifold. So it was proven in, actually, it was proven in 2013 in stock exchange math question. And it was answered by Bryant. Further, after, for example, I think maybe several months or weeks, there was a paper of Amari and Armstrong on arXiv, which was actually an extended answer of Brian from Mass Stock Exchange. And finally, last year, Brian proved this theorem for the case of smooth manifolds. Okay, and what is the actual statement? The theorem states that any analytic Riemannian metric on a two-dimensional manifold locally admits a Hessian representation. So it means that you could learn a generative model, which is and its Riemannian metric, defined as Fisher information metric, will be a Hessian of Hessian type. So the important key part of or main idea of why this could be true is the following. So what is Hessian structure actually? First is, so we have some space of parameters, which is two-dimensional. We have convex function, which is function of two variables. And also theorem states that this metric locally admits a Hessian representation. So what does it mean locally? It means that there is a local coordinate chair. For example, I say that this is function x1 of t, and another function is x2 of t. So actually, we have three independent functions of two variables, which define local coordinate chart in which we could write our metric as a Hessian of this function phi. And in two-dimensional case, we have a metric which is 2 by 2 matrix. So we have some function here g1y, g12, and metric is symmetric 1, 2, and g22. And actually, here we have three independent functions, which is diagonal components and components g12. And here we have three independent functions which define our any Riemannian metric, and here we also have three functions. So it is not that surprising that we could choose this convex potential and local coordinate chart in such a way that this metric will be reproduced as a Hessian of this convex potential as t by dxi dxj. So at least from counting these degrees of freedom, this is not that surprising that this theorem is true. But for three-dimensional case, we have in a symmetric matrix, we will have a lot more degrees of freedom than, so in three-dimensional case, we have only one new function, which we could use. But metric will have several additional components. Here we have three, and already if we look at this component, it will be a new component, and it will have not enough degrees of freedom to reproduce this three-dimensional Riemannian metric with only a Hessian metric. So at least if we have a two-dimensional section of some latent space of some generative model, we could approximate its Fisher information metric with Hessian metric. Okay, and the next question is how actually obtain this Hessian metric. What we have as input, we have a generative model, and we have some region in latent space and we have ability to sample as many samples as we want. For example, if we study a generative diffusion model, we just take some snapshot of weights from Hugging Face. We have this initial noise, and we could sample images as many as we want. But how to actually estimate a Riemannian metric? So in case of a stochastic generative model, we could ask whether we can estimate parameters based on images. And this is similar in thermodynamics. This is similar to measuring a temperature. So we have temperature, we have some distribution of microstates. For example, if this is some statistical physics model like Ising model, we have some distribution of images which are binary matrices where some spins are up and some spins are down. And we have this set, some distribution of these images. The question is whether we could find this original temperature only by looking at samples. And actually, this is the main theoretical result of this paper, which states that if we actually know these posterior distributions on the space of parameters, which are measured by samples of generated images, then the whole set of this posterior distribution, it is enough to reconstruct a Hessian metric or Fisher information metric between these distributions. So let's look a bit on illustration. So what actually this theoretical result states? Suppose that we have a generative model. We could sample as many images as we want. And then we have a function which estimates our parameters on the space of parameters. For example, it could be a grid with probabilities on the nodes of this grid, or it could be a mixture of Gaussians. So this posterior distribution is some function which takes as input several images, and its output is probability distribution on this latent space. So from now, we will work with two-dimensional sections of a latent space. And this distribution is just two-dimensional distribution. It is not so complex. It could be a mixture of Gaussians, or it could be a grid. And we want to estimate this posterior distribution based on several samples. Not a single one, but n samples. And what the main theoretical result states is that if we take many samples from our generative model, and if this number of samples approaches to infinity, then the resulting posterior distribution will depend only on the logarithm of our partition function, which is in case of exponential family distribution, this is our Hessian potential. And actually, how it depends on this Hessian potential. Actually, if we take our probability distribution on the space of parameters and it is conditioned on these input samples, we take the power 1 over n of it, and we take a limit, then it will be e to the minus Bregman divergence, with which evaluated at points t is the parameter on which we measure our density. And T prime is our ground truth samples. So we assume that from the start, we have some ground truth value of parameters, and we want to estimate it. And then we train a model to estimate the samples based on parameters. And the theorem states that this density concentrates at those parameters values which have the minimal Bregman divergence. And actually, for exponential family distribution, Bregman divergence could be just understood as a traditional Kullback-Leibler divergence. And what is interpretation of this theorem? That we have some latent space, and we have a point T prime. And we have some second point T. In our stochastic generative model, every point corresponds to some probability distribution on the space of images X conditioned on this parameter T. And this point, this also corresponds to some probability distribution. Now conditioned on parameter not T prime, but T. And actually, if these distributions are undistinguishable, for example, this is Gaussian, like this is Gaussian, but maybe here we have another point T2 prime. And in this point, our distribution of images will be a bit more complicated. And what theorem says is that if we generate images from some ground truth parameter T, our posterior distribution on the space of parameters will be concentrated around those parameters which give rise to undistinguishable distributions. So here, in every point of these red regions, we will have almost the same distribution of images. So if they are all undistinguishable, then this whole region will be the support of our posterior distribution. So this red region is our posterior distribution on the space of parameters conditioned on some big number of samples from any of those parameters in this region. Okay, and actually, let's look at a more simple case of one-dimensional distribution. So here we have T prime. I assume that this is ground truth parameters. And Bregman divergence, it measures a difference between 2 points on the space of parameters. And this is actually a difference between our convex function and the straight line, which is a tangent line to our convex function at the point T. So let's draw the whiteboard. So suppose that we have some convex function. So this is our function log z of t. And we have some ground truth value of parameters. So in this case, space of parameters is one-dimensional. And let's look at a straight line, which is tangent line to this convex function at point t prime. We see that there is a region in the space of parameters in which convex function is almost the same as its tangent line. So in this whole region, we will have almost zero Bregman divergence, because this difference between a straight line, tangent line, and the convex function itself, it is the Bregman divergence, or for exponential family distributions, it is the same as Kullback-Leibler divergence. So this is actually difference in the space of probability distributions. And here we have a region where convex function is almost coincide with its tangent line. And actually, the posterior distribution on the space of parameters will be concentrated in this region, because this posterior distribution is proportional to the e to the minus Kullback-Leibler divergence, which is the same as Bregman divergence, between any point t and our ground truth value t prime. So actually, the problem of reconstructing Hessian potential or finding a Hessian potential from samples, it could be reduced to the problem of reconstructing a convex function from a set of its tangent lines. For example, so actually, when we know posterior distribution, we actually know tangent line to this convex potential, because we know that in this whole region, our convex function will be closely approximated by its tangent lines. For example, if our t prime lies in a different point, for example, here. For example, our ground truth parameters are in this point. So the same procedure. We draw a tangent line. And now we will have a different posterior distribution. So we define a region where our convex potential is almost tangent line. So this region and this region. And we actually here have posterior distribution which concentrate near the region where convex potential coincides with its tangent line. So here we have another region where we know that tangent line is coincide with our potential, our convex potential. And this theorem actually states that if we have a probability distribution and we know set of posterior distributions, then we actually know all tangent lines to this convex potential, and it is enough to reconstruct this logarithm of normalization constant. Another interpretation is that the knowledge of all posterior distribution is the same as knowledge of this integral, which is in case of generative adversarial networks or even diffusion models is not tractable. So because it involves integration with respect to the space of images. But if we train a network that takes as input some large number of images and predicts distribution on the space of parameters, then actually we could use this knowledge to integrate our intractable partition function. And this is another way to which is different from like Monte Carlo sampling, MCMC method, or Hamiltonian Monte Carlo to estimate such high-dimensional untractable integrals. Okay, and another lemma, which just technical justification of a loss function, which we will use further to find our Hessian potential, is that if we have two functions and we only know those exponentials which are proportional to the posterior distribution, then if we have the following loss, which is convergent to zero, then it means that we reconstruct our Hessian potential up to some affine transformation, because they will have the same Riemannian metric.
Excuse me, under what limiting condition does it converge to zero?
Suppose that we have some ground truth convex function that we want to estimate. And we have a second convex function, which is from some parametric family of convex functions, which has a universal approximation property. Mm-hmm. And we minimize these variational parameters by minimizing this loss. So we minimize this loss with respect to variational parameters of this second convex function.
Okay.
And if this loss converges to zero, then actually our reconstructed function Z2, which we found by minimizing this loss, if we take these optimal parameters and take Hessian of this function, then actually it will pointwise coincide with this initial, with the Hessian of initial convex function. So in case of exponential family distribution, this Hessian is Fisher information metric, and our parametric family of convex functions, this is actually some approximation of this family of Riemannian metrics. And actually, if this loss converges to zero, then we will recover the true Riemannian metric. And it will coincide with this ground true Fisher metric pointwise. Yeah, this is the statement.
Mm-hmm. Thank you.
Yeah, but in practice, we use a bit different loss because here, for example, yeah, what the problem with this loss function? Suppose that at initial optimization stages, we will have two distributions. So this our space of parameters. I will draw one-dimensional case. Suppose that this is ground truth parameter. So this is actually defined by Z1. And at initial stages, we do not know anything about this Z1, so we initialize our parameters randomly. And as a result, we may have our distribution maybe here. And the actual pointwise difference will be concentrated on this small region. And if we use gradient descent in the space of parameters, we will not move our distribution to the ground truth one. Because gradient will, with respect to parameters of this loss, will be approximately zero. And it is good loss for theoretical proof, but it is not a very good loss for practical optimization. So actually, what is done in this paper is a bit different procedure. So we have a distribution So here the statement is about just unnormalized distributions which are proportional to Bregman divergence. So log C of t, which depends on t and t prime. So what is a better loss in space of this convex function is that we could take this unnormalized density and we just normalize it. So we know that our latent space is two-dimensional and the domain of parameters is bounded, and this integral with respect to two-dimensional variable t is actually, in our case, tractable. So we have an integral with respect to this space of parameters of the same unnormalized density. Here t, t prime, and we say that here we have s. We integrate it with respect to this dx, and here we will obtain some probability distribution which depends on z, and it will be normalized probability density. We could take the second function from our parametric family, and we'll make the same normalized probability density. And then instead this loss 20, we will use again some Shannon divergence between those two normalized distributions. And since we have this normalization, it actually will solve a problem of vanishing gradients. Okay, I will talk about the exact loss a bit later, and here a quick remark about relation with statistical physics. So in statistical physics, we have a statistical physics system, which is conditional distribution on some microstate S, parameterized by low-dimensional parameters T, and we can sample these microstates for fixed thermodynamic parameters. For example, in case of Ising model, we have this T as a two-dimensional vector consisting of temperature and external magnetic field. And here some samples from the Ising model with on n by n matrix, n I think is 128, and this is typical microstate. This is similar to images generated by a diffusion model. And we have this normalization constant, which we could get theoretically, or we could get an analytical formula. And actually, this Ising model is an example of a probability distribution from an exponential family. So in the important property of exponential family is a dependence on parameters here, for example, b and b times h. Dependence is factorized. So we have just a sum of some terms in which parameters are just multiplied by a function of microstate. And here I show images from this latent space. So my latent space has coordinates, temperature, and magnetic field, and in every point of this two-dimensional square, we have corresponding samples in high-dimensional space of microstates. And another example is totally asymmetric simple exclusion process. I will not talk exactly what it is, but it also has a tractable partition function or tractable free energy. And this is similar latent space with visualized microstates for TASEP model. here we have two parameters, alpha and beta, and we have this region where alpha and beta are larger than 1/2, and in all these regions, we will have just white noise. So in this case, just independent, identically distributed random variables would take values 0 and 1 with equal probability. And we have some crossover regions where density for increased parameter beta, we will have more dense region, and the symmetric case, but with opposite sign for increasing parameter A. And actually, if we minimize Jensen-Shannon divergence between close probability distributions, then we actually could use information about this. So we could get this Fisher information metric. I will talk in more detail about it a bit later. And the idea here, so this is similar to the idea of proof of this main theorem, is that we apply Bayes formula, and Bayes formula gives us relation between original generative model prior distribution and our posterior distribution of the space of parameters. So this is like a bit simpler justification on why knowing the all posterior distributions is equivalent to knowing original distribution. And if we apply logarithm and take gradient with respect to t, then we will see that this score function where we take derivative of a posterior distribution is the same as for original distribution. And this is exactly what is inside this Fisher information metric. And this averaging could be done just by Monte Carlo sampling. So again, important point here is that if we know this posterior distribution, we could take a gradient of logarithm of this posterior distribution. It will be the same as the gradient of our Fisher information metric, and we could just put it here, and we will recover our Fisher information metric. And also, if we have knowledge about second derivative of some convex function, we could also recover it by up to affine transformation. So this is another empirical justification of why knowledge of this posterior distribution on parameters is equivalent to knowing our partition function and this Fisher information metric. And actually, how to find this posterior distribution? So this is not so hard problem because we have a training set. So we have samples from our prior distribution. For every point, we have corresponding image or microstate, and we know the exact location of parameters for which this image was generated. And then we could just train a model which takes as input this image, outputs distribution on the space of parameters, and by maximizing likelihood, we could find parameters of this function. And after training on a data set of randomly sampled parameters and corresponding microstates, we could find this posterior distribution. And this is example of how it is done for Ising model. So yeah, as input, we have data set where parameters are sampled from our prior distribution. So in my case, this is mostly uniform. Then we take these parameters and give it to the generative model to obtain sample from the space of images. And we just train a network which maximizes likelihood of observed locations in the latent space given generated image. And how it can be done in practice, we have a lot of neural network architecture for image-to-image translation, for example, UNet, or here use square UNet or nested UNet, which is the same. As input, it takes a batch of images generated with the same values of parameters, and it returns a grid, which is representation of our probability distribution in a discrete grid of points. So if we have some domain S, we take here a square region, and we just introduce a grid. So we have a grid with discrete points, and to every point of this grid, we predict a probability, which is some number, for example, 1 divided by 20. Maybe this point has probability 1 divided by 100, and so on. And we predict this number simultaneously for all grid points, and these numbers actually define a categorical distribution at nodes of this grid. And this could be done by a single pass of this image-to-image unit, where input is some batch of microstates. And actually, this is some general approach which works for almost any generative model. And as a result, we will have these posterior distributions for every given parameter. And this is actually, as I mentioned before, equivalent to knowing all tangent lines to a convex potential. And then we take these predictions and reconstruct from this tangent line our true free energy, or by taking Hessian of it, we reconstruct a Fisher information metric. So yeah, if we manage to reconstruct this convex potential, we just take a Hessian, and now we will have access to this Fisher information metric, and then we could do usual Riemannian geometry stuff with this metric. For example, computing geodesic and computing its curvature and so on. Okay, and yeah, this is the case of exponential family distribution. We will have the following posterior distribution. And we know that for exponential family distribution, we will have almost true convergence of the statistics to the gradient of our partition function. So if we take this value and we average it, so this part is just could be replaced with gradient of log z. And here, so important part here is that if we know these posterior distributions, and if we approximate average value of this function f with just gradient of log z, then everything here is just depends on our partition function. So we don't need to do any approximation in the space of images. So this is what makes this computation of partition function a lot easier than training, for example, normalized generative model where partition function is already known. And yeah, final loss is that here we have posterior distribution predicted by UNet. Here we have posterior distribution predicted by our parametric family of convex functions. And we just minimize this Jensen-Shannon divergence, and main theorems 1 and 2, they guarantee that we will recover true Fisher metric. And this is example of this recovery for Ising model. So here are predictions made by unit, and this what was recovered by our parametric family of convex functions. And we see that they are quite similar. And here you can see results of reconstructed Fisher metric for Ising model. And if we compare it with some known thermodynamic quantities, for example, derivative of log z with respect to magnetic field will give us magnetization. So this is our derivative of our reconstructed convex potential, and this is ground truth magnetization computed from samples. And this is the same for energy, because energy is derivative of log z with respect to temperature. So we see that these reconstructed fields are actually in quite a good correspondence to these physical ground truth values. And the same is for TASEP model. So red is our approximation, blue is ground truth free energy, and here we have we can see more clearly ground truth free energy, and red part is our error of approximation. And we conclude that this is quite good. And if we compare it with some baselines, our method for reconstructing this free energy actually much better in terms of reconstructing partial derivative than other competing methods. So by evaluating this method of reconstructed convex potential on exactly solvable statistical models, we could say that it's quite good at reconstructing not only this free energy, but it's quite good at reconstructing partial derivatives. Okay, and now let's finally move to diffusion generative models. And how do we actually study the latent space? So the setup is as follows. As input, we sample 3 random points in a latent space. So diffusion model, it starts from an image with pure noise, and iteratively denoises it and generates some image as a result. And we choose stable diffusion 1.5 architecture, and we choose some generic prompt, which is high quality picture without any specific details, to study how how this Fisher metric depends in the case of samples which can come from a lot of different modes, because high quality picture detail, we assume that this prompt give rise to very multimodal distribution. So we have latent 0, 1, and 2, and then we just construct linear interpolation. So we have 2 parameters of interpolation which are A and B. They are all from 0 to 1, and we want to study latent space in this red area of our diffusion model. So more specifically, we are interested in behavior of the Fisher metric or in this latent space. So the whole steps to estimate Fisher metric are the same as for Ising model and TASEP model. So we just generate some uniform distribution in this latent space, for example, these points, for every point we generate an image, and then we train a unit to reconstruct this distribution on the space of parameters from several images generated from close points in the latent space. So as a result, we will have a bunch of known tangent lines to the convex potential, and knowledge of this tangent line is equivalent to knowing the whole convex potential. So then we just take a Hessian, and we have this approximation of Fisher information metric for diffusion models. You can see here exact components. So here we have in part C first derivatives of log z, and this is main absolute value of main diagonal components of this two-dimensional Fisher matrix. And what we see high spikes here in second components, which means that there should be something similar to phase transitions in statistical physics, because in case of Ising model, if we have spike in or discontinuity of first derivative, then we have first order phase transition, and if we have some discontinuity of second derivative, then we have a second order phase transition. And actually, we observe something similar in the case of diffusion models. And if we compute geodesics between 2 points from these different regions, we will see that straight line gives us some not so meaningful interpolation, because here we'll have additional object, which is a car, which arises in the interpolation between this post and a cat. But geodesic interpolation is more semantically meaningful for us. So we have a cat which slowly transforms for a cat which is similar to a rock, and rock then slowly transposes into this coastal view. And actually, what is interesting in this picture, and what is actually the difference between diffusion models and generative adversarial networks. On this picture, we can see some notion of phases. So we have our space of parameters, and we have regions. Here, for example, in this region, we have a cat, we have I, and in this big region, we have some coastal view. Also, this whole region represents something middle between cat and tiger, and in this region we have some picture of car, and this red region, it represents pictures of some snowy mountain. And what is interesting is that generated images, they have geodesics which are linear inside a single phase. So here you have a 2 point in this phase, and in the space of tiger/cat. So the computed geodesic is actually goes quite linearly in this phase until the boundary. Then we have some abrupt change, and it goes linearly inside the second phase to the coastal region. So actually what happens in diffusion models is that for generative adversarial networks, we will observe something behavior similar to the behavior inside the single phase. So we will have 2 images, we'll have straight line in the space of parameters, and this will coincide with geodesic. And in the case of diffusion models, if we start in different phases, inside a single phase, our geodesic will be linear. Then it will change abruptly at the boundary, and then again inside the second phase it will be linear. And actually, what happens? The question is, what happens on the boundary of these phase transitions? Actually, if we zoom in some region, we will zoom a lot until we will have just a small change of latent, which is of the scale of floating point change. So the region on this picture, which consists of like switching between tiger and mountain, changes between nearby images, it is actually only 1 or 2 minimal changes in a floating point precision. So we have extremely close latents. They are almost the same, only few entities are different by the minimal change of this floating point minimal value. But you see that actually tiger switches in completely abrupt way, and these phases, they permeate each other, so they are they don't have a strict boundary between them. And this is quite interesting behavior, which is different from what is observed, for example, in classical statistical physics model. For example, in Ising model, boundary between phases is just a straight line, which ends at second order phase transition point at critical temperature. But in diffusion models, we have a generation which is very sensitive to the small changes in this latent space. But actually, there are a lot of regions in this latent space of diffusion model in which small changes don't lead to such dramatic changes. Because, for example, inside a single phase, you can see that everything is approximately smooth. But the interesting point is that near the boundary, this change gives rise to some fractal boundary between these two different phases. And what could be the reason why this happens in diffusion models? So we could think of a simple example. So what is a diffusion model? It starts from some simple single mode distribution, and it slowly, with time tau, it transforms it into data distribution. So assume that our data distribution is some two-model distribution. So it has two distinct modes, and some new distributions are this. And what will happen if we start to take our initial samples right in the middle of this Gaussian? So in this case, this axis is our latent space T. So here we start from this point near the middle of this Gaussian, and we will go with stochastic sampling, but with a lot with all stochastic regime, but with almost deterministic sampling. So in diffusion model, you can control stochasticity of your sampling and assume that we have an almost deterministic sampling. So we have a trajectory which goes something like this and ends up in the second mode. But if we take this close latent variable and we run the diffusion inverse process, then we will end up in actually second mode. So if in real data our images, they are distinct modes, and we have a small changes in this latent space, then since we start from some almost one mode distribution, even at, for example, here maybe 0.2, something like this, even at these time steps, our distribution is close to single mode distribution. But in this region, these closed trajectories, they start to deviate because we have to end up covering all modes of the data distribution. So strictly speaking, if we have a trajectory of our generative process in this region, we will have a very high Lyapunov exponent for our diffusion sampling. Because closed trajectories, they will significantly diverge because they need to cover all modes, and these modes would be located in very different parts of this image space. So this is our hypothesis why these fractal transitions arise in diffusion models. So finally, this is a discussion. So we've introduced a method to reconstruct Fisher metric for generative models with and with help of this justification from Bryant, Amari, and Armstrong theorem, we justify that this method is applicable not just for distributions from exponential family, but for almost any generative model, because they have a Fisher metric, which is locally could be expressed as a Hessian of some convex function. And using this approach, we analyzed the latent space of diffusion generative models and discovered some interesting behavior regarding these phase transitions. And we assume that actually in reverse sampling of ODE, we have a divergent Lipschitz constant of this generative mapping, or it's the same as saying that these trajectories have high Lyapunov exponent. And this is the reason why this phase transition occur in diffusion models, but are not so visible in previous generation of generative models, like in GANs or in variational of encoders, because they cover only a single phase, and there is no such a divergence of trajectories during sampling. So yeah, I think that's all from my part, and if you have any questions, I am ready to answer.
Yes, thank you very much. It was
Is it only me who does not see question?
No, we cannot hear you, Konstantin.
Oh,
Yeah.
you cannot hear me?
Now we can.
Oh, okay. Yeah, Alexander, thank you very much for your speech. Sorry for connection issues.
For inviting.
Dear colleagues, do you have any questions?
Yeah, it was a beautiful work. I don't necessarily have questions, but we just submitted to NeurIPS a work that is quite similar to yours, but very different in different ways. So, so it was a very nice talk. We tried to actually estimate the Fisher-Rho metric as well for the denosing part of the diffusion model, but we didn't actually look at the Fisher metric. We just look at geodesics. And we added like one component. So I think what you try to do is to plot geodesic really in the pixel space. And what we try to do actually is also to add the time as another component. So we had actually our latent space is xt and t. And have you thought about? I mean, it's sorry, those questions are very random. But do you think it makes sense also to add the time component, because it's something we were discussing a lot with my colleagues?
Yeah, actually, several works which consider phase transitions in diffusion models with respect to this time axis. So they, I think, highlight three different phases. The first phase in the early steps of denoising process, where we will have almost Gaussian samples, which are in this region, they're almost Gaussian noise. Also in the late samples, in late stages of sampling in diffusion models, we have a phase in which images, they don't change much. So there may be high frequency changes, small changes in the background, and people say that it may be 0.8, something like this. And the most interesting is the middle region between these two phases, where actually switching occurs, where diffusion model actually decides what to plot, what should be result for a given prompt. So here we don't have any changes in a layout of an image, or this is pure noise. Here, diffusion model actually thinks and decides what to produce. And the last phase is like finishing some high frequency changes. And I think this is another way of thinking about phase transitions in diffusion. But in our work, we investigate what happens if we consider only x-axis as space of our parameters.
Okay, that's super cool. We didn't thought about phase transition at all, but it really makes sense to study them from this point of view. So it's a super nice work.
It is really impressive. So, Alison, did I get it right that your idea is basically look at these phase diagrams like the plots of derivatives that we have seen on probably previous slide, or Sasha, can you?
So it's this
one. Like this is actually the final state. I mean, this is the result of sampling, but we can see something intermediate. And this is also quite intriguing because Sasha has just said that the images seem to be switching in process, deciding.
On which time step this phase transitions occur. So what I know from previous work, it should be this middle phase where diffusion actually decides what to do. On this phase, these abrupt changes should start to occur, as I understand.
But on the other hand, it is great that the terminal version of this, like the final phase diagram we see, is so structured. Like we see a clear separation. We see clear boundaries. Actually,
it's actually here you see on the slide, like this linear geodesic, we got almost exactly the same result, and we were very confused. I mean, not confused, but it really reinforced the fact that maybe you shouldn't use linear interpolation if you want to keep the same semantic content across when you do interpolation between images. And I mean, Alexander, you just give like this super nice intuition about why this happens, and we were absolutely clueless about this. We were just basically trying to study not the phase transition, but maybe more the denosing process from this information geometric point of view. And I mean, we just had the deadline today, so it was a bit tough. So we didn't have a lot of insight, but this really, like, seeing that actually you can see, those phase transition to explain like this abrupt change is really, it's so insightful. So when you make your paper available online, let us know so I can read it.
Actually, about this interpolation, I would like to ask something. Could you please give us a bit more intuition on how this geodesic was computed? Like, what is the mechanism? Like, because it is non-trivial that it chooses such a way, like it chooses the point on the phase boundary. It is like more convenient to go, and it's kind of interesting.
Oh, from a diffusion model, I generate a data set of samples. So I have, for example, T. These are values in this square on picture B, which are just uniformly distributed points on a square. Then I apply diffusion to generate images, which are just, I say, DDIM sampler, which takes as input this random initial noises. And these are interpolation between three noises that I fixed. So I have a data set of parameters and images, and then I apply this method to reconstruct this convex potential. So as a result, I have a convex potential, and then from it, I derive its second derivative, which I say the Fisher metric between distributions located at different points of T. They are, so this Fisher metric is just Hessian. So with respect to Ti, Tj, and this is all components, Ij. Then if I have a curve in a latent space, then I just, so this is my latent space. As input, I give it 2 points, this one and this one. And I initialize my geodesic with a straight line. And my parameter, I want to solve minimization problem, which minimizes Riemannian length of Riemannian curve with respect to this metric.
Like minimizing the energy functional or something, or
yeah.
exactly the geodesic line.
Geodesic one. So
okay,
assume that we have only three segments. Each segment, it is a vector, two-dimensional vector. I say maybe it's V. Then I just compute scalar product V transpose our metric, my metric J, Fisher metric J, and V. So this is length of my vector V.
yeah, this is nice.
And
actually, it is squared one.
Yeah, squared one. I just sum the length of all segments and minimize the total length of this curve with respect to parameters which are points in my curve. So this is, for example, T0, T1, T2, T3, and vector V is just T2 minus T1. So I put it here, and my length is just a differentiable function of my points, and start and end points are fixed. And I just minimize by gradient descent with Adam optimizer parameters of this, just coordinates of these middle points, and as a result, I will have this geodesic. So
yeah,
if you can
now this is clear.
A lot of segments, and actually, I think there was 20 middle points, and these 20 middle points are parameters of my minimization procedure.
You mean on the image, on the picture?
Yeah, on the picture on the slide.
And one more small clarification that I would like to request is that how do we know this function is convex in the case of diffusion models? Like, is this an assumption that
This
turns out to be true? Or
for me, this is given by this theorem of Brian Tamari. It says that any Riemannian metric, then we could locally approximate it by some Hessian function. So if initial vectors are not too far from each other, but far enough to generate different images, then I could assume that locally it can be this Fisher information metric could be approximated by a Hessian metric by using this Brian Tamari Armstrong theorem.
So so we use that. We take two-dimensional sections in the parameter space. Okay, so this is potentially some kind of lens that we can use to study
we
latent
could
cases.
Different sections, because in three-dimensional case, this is not so justified why it should work, because there are counterexamples for this theorem in 3 dimensions. But yeah, we could study some slices and aggregate information across slices.
Yeah, anyway, 2 dimensions is something we could visualize way better than
usually
anything.
The phase diagram is something 2-dimensional.
Yeah, in dynamical systems, people somehow manage to study the spaces using Poincare sections, for example, which is also 2-dimensional, and still they get results. So can you do.
Yeah,
thank you.
Thanks. Any other questions?
Maybe a small one. Will this presentation be available?
I'll send the presentation after the talk. I think I'll send it today.
Thank you.
So I think thank you for listening. I think if you don't have any questions, thank you again for inviting me, for having an opportunity to present these results. Thank you for listening. And I think we could finish. Bye.